Hey everyone. Now that we've reviewed the structure of the course and a little bit of the syllabus, it's time to get a little bit into the substance of Statistics 1. For the opening week, we're going to keep it relatively simple. We're going to keep it relatively short, keep it a little bit more digestible. And we're just going to look at an introduction to statistics. What are statistics? Why do we study them? And some of the core basic concepts that we're going to see recurring throughout the course, a lot of the language that's used, some key terms that are very, very important that you understand moving forward. Throughout the lecture, like in all the different lectures that we're going to have, there'll be a series of examples that you'll be able to work through, that you'll be able to make decisions for. What I would suggest that you do so that you're sure that you have enough time to work through the example is, as soon as I read the question, I'll give a brief pause, but then I'm going to move to the answer. So while you're figuring out what your answer is to the question, just pause it. As soon as you're ready, unpause and move on. This way it's tailored to exactly how long you need. So that'll be pretty common for all the different lectures we'll have examples. On Moodle, there'll also be some additional exercises. For this particular lecture, there's not that many additional exercises needed because they're more concepts, definitional type concepts. But we're just going to, there'll be a few just to make sure that you understand the application of them. Later on in the course, as we're actually getting into formula and using different techniques, there'll be a lot more exercises for you to work through so that you get some practice implementing them. All right, so today really is about, or this portion is about what are statistics. So H.G. Wells said quite a while ago that statistical thinking will one day be as necessary for efficient citizenship as the ability to read and write. And H.G. Wells, like in probably many other areas, was right on point here. With the new economy, and particularly the advances in data that we've seen over the past few decades, understanding statistics is becoming increasingly important to be a good participant in modern society. Many of the jobs that we're getting now in all kinds of different fields, fields related to the social sciences, the business, the government, rely on heavy amounts of statistical data, where in the past it was more theoretical or based on logic, or now there's newfound data that we have where we could be building policy models off of actual views of what behaviors are, what people want, and what the actual situation is on the ground. And so because of this growing amount of data that we have available to us, we now have computers that can gather it. We also have computers that can process this data. Being able to participate in civic debates, being able to participate and come in with informed statements on many different issues, and frankly, getting jobs in an increasing number of fields requires a higher level of statistical competency than was required in the past. You know, a lot of times when we're defining the economy, we or the technological era that we're living in the past, we said maybe we're in the computing era. Before that, there's the industrial era. Right now, I would make the argument that in the 20th century, many people would say, okay, we've continued in the computing area into things like social media, the internet is the defining technology of our day. I would disagree with that, and I would actually say, and I think you get a lot of support from a lot of social scientists, that the defining, and business experts, the defining technology of our society now is data. and statistics, from Facebook, Google gathering, and so many different companies gathering, using as much data as they can about our lives to tailor products to us, to market to us, to governments, basing policy decisions off of a lot of more detailed data about social situations, to politicians using polling about just about everything to tailor policy decisions, also to public opinion. Statistics enters into our world all the time. So what exactly is statistics? And there's a dual meaning really to statistics. First is statistics is the science of collecting, organizing, and interpreting data, right? So really that's kind of what this class is in Statistics 1. We're learning about the process of using data, of using information that we have to be able to interpret it and draw conclusions based on that information. So how do we collect information? How do we organize that data? And based on the organization of that data, how do we draw interpretations from that data or from those observations? So we could view it as the science or the process of doing these things. The other version or the other definition of statistics, and both definitions are correct, and unfortunately, somewhat confusingly, people will use both definitions frequently, so you've got to be paying attention to what version they mean at any given time. Statistics is also the data. Numbers are other pieces of information that describe or summarize something, right? So statistics can be the data that we're interpreting, but it could also be the process of interpreting that data. So it's a little bit confusing. I'm going to try to use data when I'm talking about observations, and statistics when I'm talking about the process. But as you're going to see later on, we're also going to be talking about, we're going to be using quite frequently, previewing well, pretty much the next slide or a couple slides from now, sample statistics. And so if we're talking about averages for a sample, that's a statistic. So it's data that describes something, that categorizes something. So in statistics, the goal is to learn a population parameter for a population of interest, right? So let's unpack what population parameter for a population of interest. So the population in a statistical study is the complete set of people or things being studied. And really that could be anything. It really depends on your study. So it's impossible to say that something is always a population. It really depends. So for example, if we're looking at the demographic breakdown of students in this class, because we want to understand what is the background of students in this class so that we can tailor, so that I could tailor examples as well as possible to your situation. Then the population would be students in this class. If we wanted to be learning about the demographics of students at Concordia, then the students in this class would only be a portion of that population. You need to be looking at the demographic breakdown of all students at Concordia. If we're looking at the population, if we're asking about a question about Montreal, would be everybody who lives in Montreal. But if we then change the question up to Quebec, Montreal would be a sizable portion of that population. Residents of Montreal would be a sizable portion of that population, but not the entire population. Population parameters are specific characteristics of the population. So if we wanted to know what is the average age or the average life expectancy of people in Quebec, if we knew the life expectancy for everyone in Quebec, or how long everybody in Quebec lived, or if we knew the age of everybody in Quebec, if we wanted to know the age of people in Quebec, if we had the age of every single person living in Quebec, we'd have a population parameter. And then we could take averages of it. So the average age of everyone in Quebec would be the population parameter for the population of people living in Quebec. If we only had the age of people living in Montreal, and we took the average of that and said the average age of people living in Montreal is X years, we'd have the population parameter for those living in Montreal, but not for those living in Quebec. So when we're talking statistics, the goal is to learn some characteristic of a population. So the population parameter is a specific characteristic. So the goal of statistics is to learn some characteristic for a population of interest, whatever that may be in your particular study. However, generally speaking, we don't have access to the entire population. And so that makes our life a lot more difficult in statistics, but we've developed many different techniques to deal with this problem as well as we can. So instead, we rely on a sample of the population. And a sample is a subset of the population from which data are actually obtained. And oftentimes, we don't have access to the entire population for very practical reasons. It may be cost, it may be access, it may be time, it could be manpower. So imagine if our population of interest was all Canadians. Well, there's about 37 million Canadians. And so every time we wanted to learn something about them, we'd have to be talking to 37 million Canadians. Let's limit ourselves to adults so that we're not having to ask subsets for opinion purposes. So say we just want to restrict ourselves to adults. That's still, 25 million-ish people. That's a lot of people. That would be extremely costly if every time we wanted to learn an opinion, we had to talk to 25 million people. It's not feasible. And even if we had the manpower, the human power to try to get it, and we had the resources, I'm sure a lot of people would get pretty fed up if every single time we wanted to learn an opinion on something, you've got a phone call with a surveyor asking your opinion on something. People get grumpy enough when they have to do a census every decade. They got asked about something all the time, it would very rapidly get to a level of frustration. So what we do is typically we look at a subpopulation. We look at some element of that population, and based on that sample, we hope to draw conclusions to the wider population. So, for example, we refer to a census as the entire population. So you're probably used to hearing census for when you get that survey, asking a whole bunch that the government sends around. I think it's every decade, asking you a whole bunch of questions about who resides in your household. We think of that as census, but really a census would be any time you've got your entire population, and a sample is a subgroup of it, as we see in the graphic below, where we grab some element of it. When we talk about sampling next time, we're going to talk about some of the rules used for choosing who gets taken from the census. The actual measurements or observations collected from the sample constitute the raw data. So say we've decided rather than talking to 25 million people, we're going to talk to 1,000 people. And we ask them their opinion on a series of questions. And so for each of those questions, we have 1,000 different answers. All of those measurements and all of those observations constitute then the raw data. So you could think of maybe a giant Excel spreadsheet where you've got across the top, you've got all the different questions labeled. And then along each row measures a different person. Different person answers to all the different questions are listed in. This file would be your raw data of all of the observations that we've made in this particular study. Sample statistics are characteristics of the sample found by consolidating or summarizing the raw data, right? So it's difficult to learn very much from raw data, right? We've got 1,000 different people's answers. What do we do with that? Sample statistics are attempts to draw conclusions or to get something to summarize what the raw data is telling us, right? So we might say, what is the most common answer that we find? Could be one way of summarizing the data. What is the average respondent say? So before I talked about an example, if we wanted to know the age of everyone in Quebec. So say we took a sample of 1,000 people in Quebec, and we asked them their age. Well, we'd then have a list of 1,000 different ages. That's not that useful. Nobody really wants to look through 1,000 ages and try to figure out what that means. So maybe we'll take the average age and say, okay, well, this is what the average person in our sample, the average age of a person in our sample. And that would be the sample statistic for age or for average age. And we're going to unpack in the weeks that come a lot of the different sample statistics that there are. What are the options? And why do we choose certain sample statistics in certain situations, and why do we choose other sample statistics in other situations? Because they convey each different sample statistic conveys different information, and they have advantages and disadvantages. And so the best one may depend on your circumstance. It may depend on your data. It may depend on the goal. What are you trying to do with this data? So to make sure that we understand the difference between sample, population, and then parameter and statistic, right? So right now we've got a few different terms, right? We've got population parameter, population, and then we've got sample and sample statistic, right? So just to draw some parallels, sorry, I jumped back. So population parameter is the population version of a sample statistic, right? So our sample statistic, we're hoping, is going to help us to learn about the population parameter. Our sample is a subsection of the population. So the population parameter is kind of the statistic or the characteristic, is some characteristic of a population. A sample statistic is the same characteristic, but of the sample. All right, so a city planner studying pension costs determined that the average age of the 42 library employees was 54.2 years. This evaluated group is either a sample or a population. So pause it, think about what you think it is, and then once you're ready to go forward, unpause it. So again, it's a city planner studying pension costs determined that the average age of 42 city library employees was 54.2 years. This evaluated group is a sample or population. In this case, it is a population. So the city planner has looked at all of the different employees, the 42 city library employees. So got a full list of all of the employees, had their age. And so because they had the full list of everyone who's employed there, they have the entire population. They didn't take some subgroup of it and gather their ages. They looked at everyone. They looked at the full census of those who were working there. So they had the population of library employees. Just to take it a step further, the average age that they calculate there of the 42 city library employees, that average age, therefore, because we're dealing with the population, the average age of 54.2 is a population parameter, right? Because whenever we're dealing with the population and we have a characteristic, that characteristic is a population parameter. As shown in the Crime Watch article of a local newspaper, 37% of the crimes in the county in the month of September were crimes against property. The given value is either a statistic or a parameter. So pause it and think about it for a second. In this case, we're dealing with a parameter. So in the Crime Watch article, they pulled in all of the different reported crimes in the particular county. So they had the full list of all reported crimes, which means that they're dealing with the full population. When you're dealing with a full population, any characteristic of it, so in this case, we're dealing with 30% were against property, we're dealing then with a population parameter. We've summarized the crime and said that 37% were against property, so we found some way of categorizing it. A researcher interviewed a random sample of 100 library patrons as they were leaving the library and found that 54% of them had checked out books. The given value is a statistic or a parameter. Pause it, think about it for a second, or as long as you need. Okay, so 54% of them is dealing with a random sample of 100 library patrons. So if we're dealing with a sample, I mean, here it's helping us by saying it's a random sample, but we could also figure out that there's probably more than 100 library patrons who would come in anyways. So we're not dealing with everyone who's visited the library during that time period. We're just dealing with a subsection, those who were interviewed, the subsection who were interviewed. So because we're dealing with a sample, any characteristic, any summary of the raw data would be a sample statistic. So in this case, the 54% of them that had checked out books is a sample statistic. A political campaign worker wishes to conduct a poll to determine how her candidate is likely to fare in the upcoming federal election. What is the population from which she should choose her sample? A, all citizens in her candidate's district. B, all citizens in her candidate's district who are older or 18 years or older. All citizens in her candidate's district who voted in the previous election, or all citizens in her candidate's district who are likely to vote in the election. Pause it and think about this one. This is a little bit tougher. This is going to take a little bit of thinking. This particular one. So think about it and then give your best answer here. So the best answer here is all citizens in her candidate's district who are likely to vote in the election. Now, a reasonable person, A is pretty easy to eliminate. All citizens in her candidate's district, if someone's a minor and therefore ineligible to vote, this would clearly not be the best metric, the best sample for figuring out what voters will do. Our population of interest is all potential voters. All citizens in the candidate's district is not the same thing as population of voters. But remember, beforehand, we don't necessarily know. The trick for choosing between B, C, and D is that before an election, we don't know. We know everyone who's eligible to vote. We don't know who's going to vote. And that's why I said this one's a trickier question. So A is clearly not good or isn't a great option because all citizens includes many people who are not eligible to vote. So that's clearly not the right population of voters. All citizens in the Kansas district who are 18 or older. So this makes a lot of sense. Yes, there are going to be some people who are potentially in the district who are ineligible to vote for a number of reasons, but we are getting to at least we've gotten into closer to the population of potential voters. And so this answer makes a lot of sense, but it's not still the best answer because in any given election, at least in Canada, there are some countries where voting is mandatory, like in Australia. But in a country like Canada, the population that votes is much smaller than the eligible population. So it's often between 60 and 75% of adults will vote. That's a lot less than 100%. So if we want to look, if we're trying to get at the population of voters, taking everyone who's eligible isn't the best approximation there. All citizens in their candidate's district who voted in the previous election. people who vote before often vote again. It's not a bad, C is not a bad choice in many ways. It's probably a better predictor than B, right? Because there is a high turnover of voters from one election to a lot of elections. You're probably getting away with a lot of people who just never vote. But there's some people probably vote for idiosyncratic reasons the time before, and there's probably some new people who are newly eligible or who didn't care about something the last time but do care about something this time around. So this still probably isn't, if you want to be getting at the population of voters, this probably isn't your best estimate for who's in that population. Finally, all citizens in their candidate district who are likely to vote in the election. So this is a little vague, but there are metrics that social scientists have developed, particularly our friends over in political science, that have developed that identify who are likely voters. This is probably our best estimate for the population of interest in this case. Because if we want to be finding out the opinion of those who are going to vote, likely vote, the group identified as likely voters, is the best approximation to that population. This shows, though, that sometimes figuring out your ideal population can be quite difficult. And so that's always something as a starting point in any study before you can make all the different choices you're going to have to make. One of the first ones that you need to identify, and this example showing quite clearly, is that you certainly need to be aware, be sure that you've chosen your proper population. The Centers for Disease Control and Prevention, CDC, so the US agency, reports for the year 2003, 181,646 women and 1,826 men were diagnosed with breast cancer in the United States. It's a statement based on sample data or census data. So again, census being population, the entire population. Think about it, and then once you've figured out your answer, you can unpause and we'll discuss. So in this case, the CDC would be gathering data from all hospitals and all doctors across the country. So they wouldn't just be random sampling some hospitals, they'd be getting data from all of the different healthcare providers across the United States. And so this would be as close to the phone number as they can gather. So they're seeking the entire population, and we'd call this then population data. They're not taking just some subsection of looking at it and then extrapolating up. So trying to draw some conclusions from looking at a random sample of hospitals and healthcare providers, and using those sample statistics to draw conclusions about the population. Here, they're talking to everyone. And so in this case, we're dealing with population data. In May of 2007, a Gallup poll asked the following question of 1,007 people surveyed. Now, thinking about how human beings came to exist on Earth, do you personally believe in evolution or not? 68% of Republicans, 37% of independents, 40% of Democrats responded that they do not believe in evolution. It's a statement based on sample data or census data. So think about it and then come back when you've got your conclusion. So this is sample data. So usually if you see the word poll in something, you're pretty certain, or surveyed, you're pretty sure. Usually we don't do a survey of the entire population. So you're usually pretty confident that we're dealing with sample data. Also 1,007 people were surveyed, unless we're dealing with a very small town. Then that would be a very small population. So here there's a lot of different clues that could tell us that in this particular case, we're dealing with sample data. So we have different types of statistics that we use, and all of them are very important. They serve different purposes. In this course. In statistics 1, we're going to be dealing largely with the first one, descriptive statistics. We're going to be getting the basics down there, getting a firm understanding of a lot of them. Then in statistics 2 mainly, and at the end of statistics 1 to a certain extent, we'll start dealing with the second one, inferential statistics. So descriptive statistics deals with describing raw data in the form of graphics and sample statistics. So we've got our sample from our, say it's a survey. We've asked all of our respondents a question. So in that last one, say it's asking 1,007 people, we've asked questions. So we've got all of that raw data. We've got all of their answers to all of our different questions, and we've got it in a nice Excel spreadsheet or spreadsheet with whatever other program you prefer to use. Descriptive statistics are whenever we use either graphics, so tables or charts, to describe that data, or statistics to describe that data. So if we use the sample mean, so the average, if we use the median, if we use the mode, these are stats that we'll talk about in the future, standard deviation. All of these are examples of sample statistics, and their goal is to help us summarize the data. So again, looking at a spreadsheet of 1,007 observations is unwieldy, and sometimes it's much larger than 1,000. Certainly seen databases with tens of thousands of observations or hundreds of different questions. I mean, just going through that spreadsheet and reading everything would take hours, if not days or months, and drawing any conclusions from it without some way of summarizing it would be impossible. So we can use visual, we can techniques of charts, of graphs, which helps convey a lot of information in easy to digest method or manner. And we're going to be learning a lot about data visualization, but also sample statistics, which boil down the entire data to a series of numbers that are easily understandable. And we're also going to be dealing a lot with sample statistics. Inferential statistics deals with inferring or estimating population parameters from sample data. So remember, our ultimate goal is not to learn something about our sample. Our ultimate goal is to learn something about the population of interest. Even though we didn't have access to the entire population, we'd like to learn something about it. Inferential statistics is the branch of statistics that helps us estimate the population parameters. We'll never know the population parameters because we haven't looked at the whole population, but using our sample, we want to try to estimate what the population parameters might be so that we can draw some conclusions about the population as a whole. And so the branch of statistics that lets us do that is referred to as inferential statistics. We'll start touching on that a little bit at the end of this course, but it's more going to be something for statistics too. So one of the areas, and you all would have had some experience with this concept of linking sample statistics to population parameters. You all would have had some experience with the margin of error. The margin of error in a statistical study is used to describe the range of values of confidence interval likely to contain the population parameter. We find this confidence interval by adding and subtracting the margin error from the sample statistic obtained in the study. That is the range of values likely to contain the population parameter is the range of values bounded by the sample statistic plus or minus the margin of error. So there's a lot going on there. So think of an example. So say we find out that 70% of people support a given social policy. And this is in our sample, right? We did a sample of 1,000 people. We find out that 70% support a particular policy. We tell you that there's a margin of error of 2%. Don't have to know where that margin of error came from yet. that's something for later. Right now, just take it on trust that the margin of error is 2%. The margin of error defines the range of possible values where the population parameter should lie. So it's the range of values or confidence interval likely to contain the population parameter. So it would usually be said plus or minus, the margin of error is plus or minus 2. So this would mean that 70 plus or minus 2 is 68 to 72. And so once we've got this range defines the confidence interval. So the margin of error is plus or minus 2. The confidence interval would be 68 to 72. And this means, and the 68 to 72, the range of values, it defines the range of values likely to contain the population parameter. It's our best estimate of this range. The margin of error is usually defined to give a 95% confidence interval, meaning that 95% of samples of the size used in the study would contain the actual population parameter, and 5% would not. So often we talk about, because we're dealing with 95%, we deal with 19 times out of 20. So if what it means, and this is actually misunderstood a lot of times by people when they're talking about confidence intervals. What it means is that if you took 20 different samples of the exact same size, so we surveyed 1,000 people and we found 70% said this. If we did a sample of 1,000 people, right, 1,000 different people, and we calculated the confidence interval for each of them. So we took, one might have 70% agreed, one might be 67% agreed, one might be 71%, one might be 69%, one might be 71.2%. They would all have different responded because it's different people answering. If we took the confidence interval for all 20 of them, 19 of them should include the true population parameter. One of them should not. So why do we say 19 out of 20? Because 19 out of 20 represents 95% of samples. So we should expect to have probably, one weird sample that there's a little bit of difference in those 1,000 people. So if we take the confidence interval, it doesn't include the true population parameter, but 19 of them should. Unfortunately for us, whenever we're dealing with a particular sample, we don't have 20 samples, we have one sample. So you can never be certain, is your sample one of the 19, or is your sample that one that falls outside? We can never know, and there's no way of knowing without getting the population parameter, without looking at the entire population, which isn't feasible. There's no way of knowing. What we have to put on trust is, are we willing to accept a 5% chance that we have that one sample? Depending on the importance, some people may be able to tolerate, if it's not that important, if you're wrong, some may be able to tolerate a 10% chance of being wrong, right? So only require a 90% confidence interval. Saying there's 1 in 10%, there's 1 in 10 chance that your sample could be the one that doesn't include the population parameter. If it's something of incredible importance, 5% may be too large. A 1 in 20 chance of being wrong could be too much. So it may require 1% chance or 0.1% chance. By convention, 5% or 95% confidence is the norm in most of science. If it's 95 or better, we're pretty happy. If it's less than 95, we're less happy. Sometimes we'll let it go out to 90, so a 10% chance of being wrong, but usually 95 is the convention. So let's take a look in application, because I know that I just gave you a lot, so let's take a look at it with an example. So the Pew Research Center for the People and the Press interviewed 1,546 adult Americans about their attitudes about the future. Asked whether humans would land on Mars within the next 50 years, 76% of these 1,546 people said either definitely yes or probably yes. The margin of error for the poll was 3 percentage points. So 76% said yes. We have a sample of 1,546. So 3 questions or 3 tasks for you to try out. So first, describe the population and the sample for the survey. Second, explain the meaning of the sample statistic 76%. And third, what can you conclude about the percentage of the population that thinks humans will live on Mars within the next 50 years? So think about this. For the third one, there's a variety of different possible answers, but think about it, pause, give it a try, write down some answers for it, and then we'll take a look. Well, the population's all American adults, because we're drawing a sample of adult Americans, and so the goal was to find out the opinion of all adult Americans, the population, adult Americans. The sample was 1,546 American adults. What does the sample statistic mean, the 76%? Sample statistic of 70% is the actual percentage of people in the sample who answered that humans would definitely or probably land on Mars in the next 50 years, right? So we had a raw data, 1,546 people were asked to give answer to this question. So we had 1,546 answers to this particular question. That's a lot of raw data. So to summarize it, we calculate the sample statistic of 76% answered this to it. And so 76% is the actual percentage of people who said definitely or probably. And then the last question would be, what can we conclude about the percentage of population that thinks humans will live on Mars within the next 50 years? Well, in 19 cases out of 20, right, because we said that we had a 90 margin of error based on 95%, was 3 percentage points. In 19 cases out of 20, the results based on such samples would differ by no more than 3% in either direction from what would have been obtained by seeking out all adult Americans. For this sample, the confidence interval ranges from 76 minus 3 to 76 plus 3. So from 73 to 79 would be the confidence interval. Now, there's one important thing. If we had the population parameter and we knew the margin of error, based on the population parameter, we would calculate, say the true population was 78, the true population parameter. And we knew that for a given sample size, the confidence interval or the margin of error was 3%. So 78 minus 3, 75 to 81. And so we would expect 19 out of 20 surveys to fall within there. Now, because we don't know the population, so that would be the ideal usage of a confidence interval. Because we don't have the population parameter, we calculate the confidence interval around our best estimate of the population parameter. And our best estimate of the population parameter is our sample statistic. So in this case, our best estimate of the 78% is our sample statistic of 76%. And so we calculate the margin of error around there. We calculate the confidence interval around there. Our confidence interval could be complete if we are in that 1 out of 20 cases where we had a strange sample. Then our confidence interval could be pretty meaningless and won't include the population parameter, and may even be quite misleading in terms of how we judge other samples that we might do. Again, unfortunately, we just hope that we're in that 95% of cases. The same Pew survey also asked people whether they believe that humans would be cloned within the next 50 years. On this question, 51% answered either definitely yes, probably yes. Again, the margin of error was 3%, and we're using 95% confidence intervals. Can we be confident that a majority of adult Americans think that humans will be cloned in the next 50 years? So think about it and come up with an answer, do some calculations if you need, and then once you've got it, unpause. So the confidence interval ranges from 51 minus 3 to 51 plus 3, so from 48% to 54%. Given the range includes values both sides of 50%, we can't be confident that the majority of adult Americans think that humans will be cloned in the next 50 years. So we're fairly confident, 19 times out of 20, we're fairly confident that the true population parameter is somewhere between 48% and 54%. But we have no way of judging where in that range it's more likely to be. We can't say it's more likely to be 51% or 52, 53, or 48. All of them, we have no way of telling the different probability there. Based on the 95, we set our bar as 95% confident. We can say that we're 95% confident it's in that range. That's it. So does that, to be able to say that, then to be confident that a majority believes something, we would need that full range to be above 50%. In this case, it's entirely plausible based on our data that it could be 48, 49, up to 49.9, all the way up to 50%. Even up to 50% would not be a majority, which would require 50% plus 1. So it's entirely plausible that it's a minority or half, believe it, based on what we can be confident in saying. So in this case, we cannot be confident that a majority of adult Americans think that humans will be cloned in the next 50 years. It's entirely plausible that a majority does, right? Our sample statistic suggests a majority, but because a sample isn't the same as a population, there's always going to be some difference between your sample and your population. We can't be confident in it. So this is the realm of inferential statistics again, and we're not going to unpack. So in inferential statistics, you'd start learning, how do we know? So I've just been telling you the margin of error is 3%. Once we get into inferential, but I'm not telling you why it's 3%. Once you get into the realm of inferential statistics, you start calculating what is the margin of error given your sample size, given your data that you have. Sometimes it's 3%, sometimes it could be much smaller than 3%, sometimes it could be much larger than 3% to have a 95% confidence. It depends on your data. And that's the realm of inferential statistics. It's like to determine what the margin of error is. And once you start learning about inferential statistics, you'll start learning how to figure out, is it 3%, is it not? So right now we're leading up to an election. So that's why I said margin of error is something that you're probably going to have seen a lot. Every time you read data or newspaper articles about public opinion polls on the election or voting intention for people election. So it keeps going up, who's in the lead. If you look each day, you see overnight changes. So there's overnight polls for all the different political parties and voting intentions. And they change pretty much every single day. And it's hard to read into, is that because one of the political parties, if the Liberals fell 1% overnight, is that because the Liberals had a bad day? Or is that because the sample was a little bit different? So whenever you open up the newspaper articles that are talking about it, they'll always say the margin of error on this is this, and they'll usually say 19 times out of 20. right? So the 19 times the 20 means when they're talking about the margin of error, they're going within 95%, and they're saying the margin of error. So saying, if it's really, if one day the Liberals are getting 32% and one day they're getting 33%, but the margin of error is 2.5%, that change of 1% may be nothing. That could just be margin of error. Or if the Conservatives are leading the Liberals by 1%, that's really a tie. That's just because we have no way of knowing, given the margin of error, it actually could be that the Liberals are ahead by, say, margin of error is 2.5%, and the Conservatives are ahead by 1%. It really actually could be in reality that the Liberals are ahead by 1.5%. And there's no way for us to know. It could also be that the Conservatives are ahead by 3.5%. There's no way for us to know given the data we have. So in that case, you just have to say, right now it's a statistical tie. Finally, the process of a statistical study. So determine the population you want to study and exactly what you'd like to learn about it, right? So again, remember from our example of when we're choosing in our example about wanting to learn about voting intentions in a particular district, right? Who is our population? Well, that was actually a much more complicated question than somebody would think, might think. And exactly what do we want to learn about it, right? What is the parameter of interest for us about the population? Then once we've got our population, choose a sample from the population. We're gonna learn a little bit about sampling next time. Then collect raw data from the sample and summarize these data by finding sample statistics of interest. We'll learn more about sample statistics later on in this course in the coming weeks. Use the sample statistics to make inferences about the population. We're not going to see too much about how to do that in this course, but that's something that will be coming. And then once we've made our inferences, we'll be able to draw conclusions. That's all for today. Nothing too long for starting off this week. There's not too many exercises, but they'll help reinforce some of the conclusions, particularly with confidence intervals, where you may want some practice. There's a few more there to help you out.